Welcome to Session 3 of the Maximum Likelihood lecture. In Session 2, we showed that the estimator is consistent and asymptotically normal, and that it has, as shown here, an asymptotic distribution normal with a mean of the true value and a variance that can be considered 1 over n, the inverse of the fish information matrix. So let's talk briefly about how to estimate the variance. Obviously, estimating the parameter itself, well, that's maximum likelihood estimation. So that's the whole point of this of this lecture. But the question remains, how do I estimate the variance? So if you remember, the information matrix is the expected value of the outer product of first derivatives of the log likelihood, or it is the negative of the expected value of the second derivatives of the log likelihood. So we'll use the sample moments for this, right? So I could say that one estimator is going to be the sample moment of the outer product, keeping in mind that I can calculate for the log likelihood for each observation in the data. Technically, it's each independent observation in the data. Its derivative, and so I can get a whole vector of these derivatives across all of the samples, multiply it by the transpose of that vector, and we will get the outer product of those derivatives. Or I can calculate the Hessian matrix, essentially for each individual in the each independent observation in the data set, and then sum those. So we either have the 1 over n, the sum of the outer product, that's giving me a sample moment representation of this expected value, or I can take negative the sample average of the matrix of second derivatives, which is going to give me the sample moment parallel to that one. So we have two estimators. We have the first estimator, just as I said, is using the sample moment for the information matrix, and then taking its inverse and taking 1 over n, right? Why am I doing all of that? If you remember, it is 1 over n, the inverse of the information matrix. So I get my information matrix here, which I plug into here, take its inverse, and 1 over n, which, if you'll notice, I've got 1 over n outside the inverse, and 1 over n inside the inverse, so they collapse and disappear, and I really end up with my estimator as the sum of the outer products of the derivatives inverted. This is the estimator that the BHHH algorithm will depend on. Another one is to take this negative sample average of the second derivative matrix. I get the second derivative matrix for everybody in the data set, and then I sum them, and I take the average, take its inverse, 1 over n, which again, the 1 over n's reduced down, and it comes down to the negative of the sum of the second derivative matrices across independent observations in the data set, inverted. This is what Newton-Raphson algorithm is going to use. It's calculating the approximation to the Hessian matrix. So the first estimator is called the outer product of the gradients. You will see in Stata it will be denoted in the table of results as OPG. And the second is called the observed Hessian. And in Stata they don't designate it separately. It will literally just, when it uses the observed Hessian, it will just simply state the variance or standard error based on it. Now, it's harder to calculate the second one, which is, say, the Hessian, because you have to deal with second derivatives and calculating second derivatives. It takes more kind of equation-type work to come up with the second derivatives. Or if you're going to use a numeric approximation, you have a lot more calculations to do in order to get the numeric differences in the differences, which is what you use for the observed Hessian. But it, in smaller samples, is going to give a better estimate, assuming that it is positive definite. It's not guaranteed to be so in any given sample, but assuming that it is, it'll give you a better estimate than the outer product estimator in smaller samples, as they both get large asymptotically, they converge to the same thing, right? Because above, as we notice, the variance is equal to the limit of both of those. So they would be fine. And so when you want to use the Hessian matrix to give you your standard errors. Practical sense, and we'll do this later on in the course, you can run your optimizer using, let's say, BHHH, and it's going to be using that some form of the outer product to find the top of the hill. And so there it's instrumentally just simply finding the top of the hill. We really don't even care for it as a variance estimator. It's just a way to get to the top of the hill. And then using those results, you plug it into the maximum likelihood estimation again, starting there, and tell it to do Newton-Raphson, and then it will pop out the standard errors associated with the Hessian matrix, and that would be typically a better standard error than just depending on the final outer product standard error. There is another one called a robust estimator, and that basically puts these two together. You take the inverse of the Hessian-based one times the outer product times the inverse of the Hessian. Asymptotically, they're the same, so they cancel out and you get the inverse of the Hessian, which is the variance. The advantage of doing this, and I won't go into it, but there's a paper by White that shows that this is a robust estimator because it gives you the correct standard errors for the maximum likelihood estimator, even when the model is misspecified. And this is an advantage if you feel that your estimator is not, rather your likelihood function is not really necessarily properly specified. There's some component of it that you're concerned about. You can use the robust estimator, which also called the sandwich estimator. You can think of these as your slices of bread, and there's your stuff in the middle, to at least get you the correct standard errors for that estimator. Of course, you got to keep in mind that what you're doing is you're saying I have the correct standard errors for an estimator that is converging to a value that isn't the one that I want anyway. But nonetheless, it does, as an estimator, there's another proof that you can go by that says that the maximum likelihood estimator of a misspecified model will give you the best misspecified model. So you would have the best misspecified model and the proper standard errors associated with them. So that's a technicality, but we use this quite often when we're concerned with heteroscedasticity or certain types of misspecification that we have not been able to handle. So how would we calculate this? Well, let's suppose you created variables associated in your data set associated with each parameter in the model. So here's variable 1, variable 2, variable k if you had k parameters. And for each individual, 1, 2, down to the nth observation, you calculated the derivative of the log likelihood with respect to the first parameter for everybody, and then with respect to the second parameter. So the variable 1 has to do with the derivative with theta 1, variable 2 has to do with the derivatives, and you do all of these and you create this as a matrix. Think of it as new variables in your data set, and indeed that's what you could do, is you would create new variables in the data set that contained each of these. Well, this sum of the outer products is just G transpose G. So the OPG variance estimator is G transpose G inverse. In Stata, how would you do that? Well, once you've created these variables, you could type mat accum G. It's going to label, you could put Fred here. This is just an arbitrary label for the matrix. Type in that variable list, go comma no constant because you don't want Stata to automatically add a vector of ones. And then say mat V is equal to sim inverse G transpose times G, and that will give you the outer product variance estimator. Two final points to consider. One is that the maximum likelihood estimator is asymptotically efficient. So if it is a correctly specified function, then asymptotically it is the efficient estimator. Second, and this is actually very important, and that is the maximum likelihood estimator is invariant to transformation. So you can get an estimate of a function of parameters by taking the function of the MLE estimates. And that will be the maximum likelihood estimator of that function, which makes it very easy to evaluate other types of features of interest that are functions of the parameters, because a function of the maximum likelihood estimator is actually a maximum likelihood estimator of a function. You could think of it that way. So this is a advantage of MLE as well. So two kind of nice advantages to MLE that in many respects are much more important than some of the asymptotic ones, although I guess this is asymptotic too, is that it's efficient, and really what's good is that it's also invariant to transformation. So this is a brief session, but this is the completion of session 3 of maximum likelihood estimation.